Hey, good afternoon. It's lecture time. I see that I'm 1 minute late, but I think it is okay. lecture number, let me see, lecture number 5. So it's a week 6, lecture number 5. And what will happen today is that we're gonna kind of what happened last week was that we were about to approach the climax of this course, and today we're gonna have the climax, and the climax is eigenvalue analysis and modal reduction. Modal reduction in particular. This is something that is a little bit of mind-blowing. So it takes a little while to get the concept, like, how the modal reduction behaves, because we're going to move from one set of coordinates to another set of coordinates. But this is kind of what we are used to deal with. Because remember in a fall course, we were moving from one set of coordinates, global coordinates, to generalized coordinates. And today we're going to introduce mapping too. Not the same kind of mapping, but a little bit of different kind of mapping. And once we're done with the climax, then there's going to be one more lecture, which is next week, Wednesday, prior to midterm exam. And next week, Wednesday, we're going to kind of closing the case of modal reduction techniques. And I'm going to offer you a summary about the matters that I'm expecting you to master when you're entering the midterm exam. And if there's going to be any time left next week, Wednesday, I would like to discuss shortly about career counseling. Remember, this is what I promised to do. Yeah, this is what I wanted to do. This is what I kind of insisting to do, because I feel that there are a few things that I would like to share with you, and there are a few things that you can learn from me in career perspective point of view. And if we have a time, I would like to open the topic next week, Wednesday. If not, then we're going to save that topic for lectures right after midterm exam. Okay, so let me make a minor settings here. So I'm going to move my computer to be a bit closer to me. So it's still looking good. Okay, so eigenvalue analysis and then modal reduction. Those two, they're kind of like brothers, because we do need both. We do need eigenvalue analysis to conduct the modal reduction. Although there are other techniques to carry out the modal reduction, I mean, other than the ones that are based on eigenvalue analysis, but many are, one way or another, based on eigenvalue analysis. All right, so shortly what we discussed last week. So last week we opened a very important topic about finite element modeling. And the finite element modeling is all about, okay, there's a question. So let me answer that question before I'm moving on this summary. The question is, when will be midterm exam? And midterm exam will be not next week, but week after that. And more specifically, if I remember correctly, this is coming from my heart. And maybe my recollection is not correct, but I am thinking that it's going to be 2nd of March, which I think that it is a Tuesday, and it's going to be at 4 p.m. You can check that out by logging into a website that is uni.lut.fi, if I remember correctly. So the address where you can check it out is this one, uni.lut.fi. Okay, so others, if you have a better knowledge that I do, though, please let me know. Okay, so anyways, so last week we discussed about the finite element modeling. And one of the important things in a finite element modeling is that how is that we are estimating particles between the nodal location to behave. And this is, okay, there's another question which I'm also going to answer. This is also related to midterm exam. And the question is that, do we need to register the exam? No, you don't need to register, because the exam will be in Moodle. The instructions, practical information will be provided to you next week, Wednesday. But basically how it goes such the way that the exam will be organized via Modal. So you log into Modal site, like you're checking the lecture material and other material of the course, and then there will be a midterm exam. And once you click the midterm exam, there will be a certain number of questions. And then many of the questions are essay type questions, so you just write your answer, and then once you're done, then you submitted your exam paper, exam website, or however you wanted to say it, to a system, and then whatever I have a time, I will check your answers and I will grade it. And of course, I would like to do that in a timely manner, but we'll see how it goes actually. No need to register. And again, you can check it out when the exam will be in details. You can check it out from this address. So it's uni.lut.fi. All right. Any other comments, questions regarding midterm exam? I guess not. All right, so let's go back to finite element modeling. Now, like I was about to explain, the finite element modeling is all about how is that we are predicting particles between nodal location to behave. So that's an essence of finite element modeling. So it's not about, that we have just a nodal location and then there is an empty space. There is a black space, a black box between these nodal locations. Not at all. It's completely opposite. It's all about how is that we are predicting particles between the nodal location to behave. And then it's kind of the way that it is materialized, the behavior is materialized, or how it is actually is expressed is in terms of nodal degrees of freedom. So if you have, say, an element with the two nodes, and this is obviously a beam-like element, and this beam-like element, there's a line that connects these two nodal locations. Now, if you're going to introduce a displacement to, say, this direction, obviously this nodal location is going to move here. So it's all about how is that the particles that are between these nodes, how is that they behave. And the best way to make a prediction about the particle behavior is to use polynomials. You don't necessarily need to use polynomials if you don't like the polynomials, but they're very popular. And they're very popular because they're easy to differentiate. And we do need this differentiation. So we need the partial differentiation, and they have other mathematical benefits. But if you're not happy with the polynomials, you can use the trigonometric functions, or you can use pretty much whatever you want. You could use NURBS, non-uniform rational B-splines, which, by the way, is a new kind of technique in a finite element modeling. I will get back to these NURBS and how the NURBS could be used as a base function for finite element modeling a bit later. And it is related to CAD softwares and how to do the meshing. But let's leave that topic a little bit aside and let's focus on conventional finite element modeling. So the conventional finite element modeling is all about how the particles between the nodal location is expecting to behave. All right. Now, how is it you can select the proper polynomial? Well, of course, it depends on what kind of element you would like to predict. Now, if you have an element like, again, let's go back to this beam-like element that consists of two nodes, and each node have 2 degrees of freedom, which are displacement in a transverse direction and rotation. Then this element will have a total of 4 degrees of freedom. So then you need to predict this by using 4 unknown polynomial coefficients. And how you can select those, that will come from this famous Pascal triangle. The Pascal triangle that tells you how is it you can possibly select these polynomials. Now, let's say that if there's going to be a node in the middle, and the node in the middle only have 1 degree of freedom. And the 1 degree of freedom would be, say, displacement transverse direction. That would mean that you need to modify the polynomial such the way that there have to be one additional component, and one additional component would be a4 multiplied by x power 4 or x power 5. But still one additional component. because remember how it goes? It goes such the way that if this is a Pascal's triangle in two-dimensional space, I'm going to leave it here. I'm not going to write it anymore component. You could select all the components like in a line. So you could start it here in the top of the pyramid, and then you go down and you select each one of the components in a way. That's one way to do it. But only the kind of like the minimum requirements you have is that you have to select this guy here and this guy here, because this guy guarantees that your element can describe rigid body motion, meaning that you can place your element any position, any orientation in the space, and is not producing any strain. And then this guy here guarantees that the element is capable to predict a constant strain, which is also needed. Then the rest you can select as you want. Now here we selected in a way that we selected this one and this one. And this triangle goes down, as far as you want. So it could be possible that instead of selecting this guy here, I could select x power 5. What that would mean? It would mean that these shape functions, which explaining how the element can deform and how particles are following the deformation that takes place in a nodal location, these shape functions will be modified. So that's going to be the consequence if not selecting these in a row. So is it going to be better or worse? Well, that is a more difficult question to ask. It could provide some important additional features if you're not selecting the polynomials in order, but to make sure that your element is capable to converge and is converging from the same direction all the time, it may be a good idea to select all the polynomials in row. Okay, sorry that I'm plugging the view again. So the x power 5 is the one that is here. Okay, here it is. So here's an example. So this is where I choose the polynomials to be not selected by the order that they appears in Pascal's triangle. So you see that I have here the constant value, I have the x value here, but then I'm skipping x power 2, and instead of having x power 2, I have here x power 3, and then the final component is x power 5. All right, so what is the consequence? Well, the shape functions will be different. You see that the shape functions will be now higher order polynomials. Are they any better? Well, not necessarily, but they look different. Now this time, still it's valid that the shape functions are describing how one nodal degrees of freedom is affecting the element deformation. Here is an example. So if again I have this beam element 2 node, first degrees of freedom is moving this node in a transverse direction. You see that that's what exactly happens here. Tangent here is 0, displacement here is 0, tangent here is 0. This looks a little different when comparing the previous set, and this is a rotation of same node, and these are the mirror images. So kind of like how they look different. This is summarizing that. This is what I use as a conventional way, and this is my additional way. But of course, you would like to know which one is better. Well, like I said earlier, to play safe, it may be a good idea to select the polynomials in order, like this. But some of the good performing elements are actually the elements that you don't select all the polynomials in order, but you are skipping some of the components that you are using the higher order polynomials. And obviously, this is affecting how the element can deform. Like you can see, this looks a little different than this one. So it may come with a certain benefits. And in certain cases, I cannot say like all the cases, but in certain cases, you can improve the convergency by selecting, or let's say skipping, some of the polynomials and replacing the low order polynomials by higher order polynomials. And again, convergency means that if this is a number of elements, this is a solution that is correct solution, it means how fast you can reach acceptable solution. Like how many element is needed. Shorter the length, I mean, less element you need, better the convergency rate. And of course, you would like to have as good convergency rate as possible. And that's simply because then if the convergency rate is good, it means that you can be using, I mean, that your computational efficiency will be enhanced. It will be better. Okay, so the polynomials tells you, no, polynomials, and then the one thing that I forgot to mention here is that what we do here with polynomials is that we wanted to re-express the unknowns of the polynomial by nodal degrees of freedom. And once you do that, then you get this safe function matrix. This is critical step. I could use polynomial like it is expressed here and solve my unknowns, which will be the A0, A1, A2, A3, and that's going to be the way to solve the problem. But these A's do not have a clear physical interpretations. So to get the better physical interpretations, it is recommended and is always made in finite element modeling to replace these polynomial coefficients by nodal degrees of freedom. And when you do this trick, when you do replacing A's by nodal degrees of freedom, you get the safe functions. And safe functions are telling you how element can deform. How element can deform. Okay, now put the Netflix aside, put browser aside, and listen to me. Safe functions are telling you how the element can deform. So it is predicting how particles between the nodal location are moving if there's going to be a displacement or if there's going to be some changes in nodal degrees of freedom. That's what the safe functions is doing for you. Okay. So physical interpretation of safe functions shows the way that an element can deform. Well, it should not be S here because it's a polar. So defines the rotation of a particle. That's option number B. Defines the strain displacement relationship. No clear interpretation, no clear physical interpretation. So A shows the way that an element can deform. Defines rotation of a particle. That's option number B, a B option. Defines strain displacement relationship. No clear interpretation. And here's my mouse. And the Socrative is on, and the game is on. So please enter your guess about the success rate. I see that I have 42 students. That sounds like a suspicious. That it cannot be that many. I see that I have 41 viewers. Yeah, 41 viewers, and game is on. Oh my God, I like this. I like the answer 100%. But unfortunately, I don't believe it that by myself. My guess is this 75. I know that somebody else was guessing the same number, but I'm with you. So I'm also with 75%. 75%, and let me see how are we doing. 17 answers. And I'm collecting more, so it's 19, 20. Let me see, how can I? All right. So here is a in-class quiz. Gonna wait a little while to ensure that each one of you will have an opportunity to answer. Okay, 25. And I said that we have how many viewers? 31. So I'm expecting maybe 6 more answers and then we're done. Okay. And then we will continue with the finite element discussion. Okay, let me change my view a little bit. Okay. 26. Maybe that's 27. All right. So I'm expecting that. Maybe that's going to be then 28. Okay. So we pretty much done. But 100%. 100% would be really, well, you know, that would be like winning in the lottery. Um, I don't know. It would be really outstanding to have 100%, but I don't think it is gonna be today. For some reason, I feel that it's like another usual. It's like another usual Wednesday. It's not the special Wednesday. I don't have that vibe in my head, so we'll see. We'll see. And I need to make sure that I have a paper ready to make a notes like who is a winner of this lottery. Okay, so we have 29 answers. So I'm gonna close the case. Okay, so I got all the guesses. So the correct success rate is this one. Oh, what is this? So is that is missing the colors now? Oh, look at that. I don't know why. So it seems that they changed the user interface a little bit in in the Socrative. Anyways, the correct answer is 90. So it's 90% success rate, which is great, which is absolutely great. And we got the exactly correct number here. I can see that. Oh, we have many. I can see. Let me see. There is a one winner. And again, I'm not going to pronounce the name of the winners, even though that it will be a lot of fun. But you know, to make sure that I don't release your identity, I'm gonna just write it down. Where was another one? That was another one. Did we get more? Okay, what you guys say? 92, would that be okay? Yeah, let's put the 92 also as a part of the winner. Okay, so now, as promised, let me see if it disappeared. Hmm. So what happened? Oh, I'm sorry, I clicked the wrong button. So now it is the correct button. All right, so next week I'm going to explain a few more details about the finite element modeling, like how to place, how to structure, how to build a mesh mathematically. And mesh means that it's a structure that is described by number of elements. And I can see that for some reason my screen is a little bit moved. Okay, so let me put it back where it's supposed to be, like this. All right. So and also a little bit about how the element orientation can be accounted. So those are like a minor, well, not minor details. Of course, they're important details if you really want to use a finite element modeling. But for our perspective, they are a little less important. Now, what happens in finite element modeling is this, that you get started in your finite element modeling by first selecting how many nodes you would like to describe, or more specifically, what is your number of degrees of freedom. Once you get your number of degrees of freedom, then you express your element behavior by using polynomial expansion. But all polynomial unknowns are a little difficult to deal with, so that's why you want to convert to unknowns to be expressed by using nodal degrees of freedom. Once you have the nodal degrees of freedom, then you get these safe functions, and the safe functions are telling you how the particles between the nodal locations are expecting to behave. All right. Well, this is information you need, and this is pretty much when you stop thinking and you start using your mathematical skills mechanically. So then using this information, you can derive the relationship between the strain and displacement. And then you can express your stiffness matrix and you can express your mass matrix, which is your inertia description. And even with help of safe function, you can express how the distributed load or the load force, to be more specific, load force, force that is not in the nodal location can be expressed in terms of nodal degrees of freedom. And that's the way you can make it that happen. All right, so finally, the equation of motion looks like the one that is shown here. Okay, let me take this off to make this a bit more clear. So we have here, again, we have um, kind of like a Newton's second law. So we have inertia forces here, which is mass multiplied by acceleration. We have here external applied forces expressed in terms of nodal degrees of freedom. And then we have here elastic forces, which is a stiffness matrix multiplied by nodal degrees of freedom. Now, what you can do with this equation is that you can simply take it as it is and solve it by using direct method, which, well, the method that I'll typically refer to as a direct method, meaning that you do no modification to equation of motion, which again is this one here. This is your equation of motion. So how you can make it happen? Well, of course, you wanted to get this one here, which is a acceleration of nodal coordinates, and that's you can use to integrate velocity of nodal coordinates. And once you get the velocity, you can get the position. So that's how it goes. So like in multi-body dynamics. And that's how finally the equation of motion, that this is what you can start integrating in forward of time. And this is not gonna fly. This is not gonna work out. And the reason is that typical finite element model is having a large number of degrees of freedom, really a large number of degrees of freedom. So the number of unknowns, meaning the nodal degrees of freedom, could be easily 10,000 degrees of freedom. It can be 100,000 degrees of freedom. It can be 1 million degrees of freedom, 10 million degrees of freedom. And if you have that many unknowns, it's not reasonable to solve that many variables every single time step and then take this information about the deformation and put it in a multi-body dynamics. That is not just computationally feasible. It's theoretically possible, but it's not making any sense. So it's not what you can do in a daily life, in a daily dealing. Not simply possible. So that brings us a very important topic. And that very important topic is about modal reduction. So we need to reduce the size of this problem. Size of the problem meaning specifically how many variables we're dealing with, how many unknowns we're dealing with. And what we could do, so if we're thinking about, what is theoretically possible, well, we could use a coarse mesh. We could reduce the number of elements. That's possible. But remember the nature of finite element modeling. The nature of my finite element modeling is this, that if this is a solution that you're aiming for, you get better and better solution when you're increasing the number of elements. So that's a kind of the dead end. Because if you say that, okay, I want to make this computationally more efficient by using less elements, you end up to have a solution that is not correct solution, is not according to reality. So that's not the good choice. So we need to do something else. And something else that we will do here is that we're gonna leave the nodal degrees of freedom away. So we're gonna forget about the nodal degrees of freedom. And we're gonna move from nodal degrees of freedom to something else. And the something else that we're gonna move will be modal degrees of freedom. All right, so that's what's gonna happen. All right, so this is pretty much what I just explained. So usually, finite element model consists of a large number of degrees of freedom, and it makes it very difficult to solve this. That you can solve it in, with a certain short period of time, but put that as a part of the multi-body code, that's going to be almost mission impossible. And reason being that the multi-body simulation typically spans over the long period of time. And you cannot really use your finite element modeling as it is, as a part of your multi-body code. Okay, so we need to do something. So we need to reduce the size of the unknowns. And here are the questions. So these are the questions that I'm, by the way, sorry. So these are the kind of like from the previous case. So explain the polynomials. We covered that. The role of the Pascal triangle. We covered that. Convergence rate. We will get back to this next week when we are preparing us to read an exam. All right, so here it is. So this is what we're going to do. Now, again, please take your I don't know, YouTube or whatever you're browsing currently, put it in aside because this is extremely, extremely important to understand. And it's going to take a little while to understand the concept. So I'm going to explain this several times, but please follow my first time when I'm explaining this because if not, this is going to be very, very rocky road when we're proceeding in this matter. So put everything in aside and focus on me, just me this time. Okay. So first, mathematically. So what's going to happen when we're reducing the number of unknowns? What's the method that is more feasible than using a less elements? Well, the more feasible way would be looking at the ways finite element model can deform. Not just a single element, but the entire structure can deform. And you know that if there is 100,000 degrees of freedom in your finite element model, it essentially means that your structure can deform in 100,000 different ways. 100,000 different ways. All right, that's the important thing. So there's going to be a lot of different ways that the structure can deform. Well, all those means of deformation and all these ways of deformation important? Well, not necessarily. Not necessarily. This actually gives us an opportunity to actually reduce the problem. You know that if you have again finite element model, which says let's just give an example here. If I have a finite element model, this is a beam structure again, and I have here 1, 2, 3, 4 elements. 4 elements, each one of them has 2 degrees of freedom, so it's going to be 8 degrees of freedom. So it means that there's going to be 8 different ways that this structure can deform. And you can find these ways by conducting an eigenvalue analysis. An eigenvalue analysis is going to give you eigenvalues, which are natural frequencies, critical frequencies when the structure will vibrate, and corresponding deformation modes. Okay, 8 different ways. How many are really important for us? Well, of course, this is a case dependent, but not necessarily all of them are important. Maybe in a case of 8 degrees of freedom, all of them are playing certain critical role. But if you have 100,000 degrees of freedom, it becomes to be clear that some of them are less important. I mean, that some of them are more important than others. And this gives us a possibility to reduce the number of modes, number of deformations that are within the structure. Okay, so this equation here shows that the nodal degrees of freedom can be converted to be modal degrees of freedom. I know that this sounds to you like modal, nodal, you know, I cannot get the difference. And you don't. But I'm going to use a little bit of time to explain you this in a little bit of different way. But you leaving nodal degrees of freedom and you start looking at modal degrees of freedom. And not just all the modal degrees of freedom, but some of them. This is going to be the trick. This is going to be the inherent, or kind of like the bottom line, the core content of the modal reduction. Because it's possible that the P here is having less unknowns comparing to U. What it means. All right, so let's take a look at an example in a second. So that should shed a light to this particular feature. Okay, so these are the questions, and for some reason my slides are again a bit twisted off. So let me see what I can do for you. Okay, so I'm back. So before we proceeding in the matter, these are the 4 questions that you may or may not find in a written exam paper. Okay, so physical interpretation of eigenvector. I'm going to explain that to you in a second. Physical interpretation of eigenvalue. That too I'm going to explain to you. How to conduct an eigenvalue analysis. Maybe this should be another way around. So first we do eigenvalue analysis, and then we get the results that are in a form of eigenvalues and eigenvectors. Anyway, so how to conduct an eigenvalue analysis, and what the mass normalization of eigenvectors, what that means. Okay, so let's look at this relation between the modal and nodal degrees of freedom. Why is this keep on jumping to different locations? That's a little bit annoying feature. Let me lock that here. Hopefully it stays here too. Okay, so here I have a cantilever beam. Cantilever beam which is attached to ground by fixed constraint, or let's say that there's a boundary condition, because the boundary condition, that's what they call in a finite element community, is introduced such the way that this node here cannot translate and it cannot rotate. Okay. Then I have a free end of the cantilever beam, and again in the free end of the cantilever beam there is a pin force that is loading the free end. And I'm modeling this beam structure by using 1, 2, 3, 4, 5 elements. All right. So what is important for us is how is a number of degrees of freedom. And this time it's going to be nodal degrees of freedom. Let's say that we have again this beam element that consists of 2 degrees of freedom. So this one here has a 2 degrees of freedom, 2 degrees of freedom, 2 degrees of freedom, 2 degrees of freedom, and 2 degrees of freedom. So it is a total of 10 degrees of freedom. All right. Now what we could do here is that we can solve the static deformation of this free end, this U here, by building the stiffness matrix, taking all these 10 degrees of freedom into account. This will be a vector that consists of 10 degrees of freedom. And then, this will be the point force that is associated with 1 nodal degrees of freedom. So this could be solved easily by converting my stiffness matrix like this and multiplying that by a corresponding force vector. So what we're going to get as a result will be, each one of the displacement, these nodal displacement. So this one here will have 10 unknowns, like I mentioned already a number of times. I could do this a little bit a different way. And I could do this in a different way, in a way that I could first conduct an eigenvalue analysis to this cantilever beam. An eigenvalue analysis means that I'm looking at the ways the structure can vibrate. Maybe it would be easier to say the ways that the structure can deform. How much they can deform in that particular way, that will remain unknown for us. Now that's going to be called something like amplification factor. And we're going to solve the amplification factor instead of the nodal degrees of freedom. All right. Now this is the climax of the course. So follow me carefully, as carefully you can. All right. So I'm going to change the color. Now I could just take this cantilever beam and I can look at how are the lowest deformation, lowest natural frequencies and lowest deformation modes associated to those frequencies. So I could have like deformation like this. All right, this is telling me how the nodal degrees of freedom are moving with respect to each other. So this is a way structure can deform. So it's telling me that if this is moving this much, then these other nodes are following roughly the base of my drawing here. This is one deformation mode. How much this is actually contributing to the final solution, that I don't know. That's going to be called as a question mark number 1. All right. Second deformation mode could be something like this. And again, it's telling me how the nodes are moving with respect to each other, like the ways they move with respect to each other. How much they actually move with respect to each other, I have no idea. I don't know. But let's call that magnitude as a second unknown, as a question mark number 2. And then I can keep on doing this until I reach this 10 degrees of freedom. But now that really the big trick here is that instead of using 10 deformation modes and corresponding question marks, I could use just some of them. Let's say that I'm going to use 2 of them. And when I'm using 2 of them, I can build this relation. This is my nodal degrees of freedom. This is my modes, my unknowns, which this time would be unknown number 1, unknown number 2. This one here is a numerical representation of ways nodes can move with respect to each other. The ways they can move with respect to each other. Oof, that's hard. It is really, really hard. I know that I don't. Let me see if you guys are still there. You're still here. Oh, that's a good news. Okay, so then sorry that I missed. There was a comment earlier. So why 2 degrees of freedom? Yeah, well, you could use more degrees of freedom per node allocation if you're not happy with 2. But I select 2 because this was an element that we looked earlier. This was an element like, let me go back here. These say functions are describing beam element which consists of 2 nodes, and each one of the nodes has a 2 degrees of freedom. And these 2 degrees of freedom are movement in a transverse direction and rotation, like this. I could also have an axial direction here. That's going to be okay. I could have here a node in the middle. All that is possible, but I just select that as a one option. But to answering the question, no particular reason. I could use another type of the element. That shouldn't change the story at all. So it should be all the time same story. Okay, so we here. Now, how is that we can get this? Do you guys have any other comments, questions, or should we save it for team session? We could save it that for the team session. Okay, so let's go back to the equation of motion. This one here. Where is it? This guy. Equation of motion. And again, like the one way to look at this equation of motion is that components in a right-hand side of the equation is telling the loading condition, whereas the components in left-hand side of the equation, which is a mass, inertial forces and elastic forces, those are telling the feature of the structure itself. So what we could do then is that we could get these possible deformation modes by focusing on the structural properties only, leaving the force with no attention. Okay, how is that? There is a question, another question, which is extremely good question. Like, first of all, there is 2 degrees of freedom. How we understand the degrees of freedom here? The degrees of freedom is that what is, if you have here beam element, what are the ways that these nodal location can have a displacement? Oh, sorry that my head is blocking the view. So let me make drawing to be a little bit of different location. I'm kind of happy with my green screen and everything, but the problem is that I keep on blocking the view. And even though that I'm reducing the size of my head, that still happens. So beam element is here. Degrees of freedom means how these nodal places can have a displacement. So if I say that I have degrees of freedom that are this one and this one, if I introduce the force that is axial direction, that's not the degrees of freedom. So there is not going to be deformation whatsoever to that direction because it's not my degrees of freedom. But if I would use this as a cantilever beam like this and introducing the loading in a transverse direction, sure, then this would be, translation and rotation at this end. So that's what it means. Hopefully it's clear. We could discuss that a bit more in a team session if you guys want. All right, but here was my explanation. So I was here to say that, okay, this equation we have a loading in the right-hand side. Left-hand side, we have a feature of the structure. The feature of the structure, loading. And now these deformation modes, we can figure it out by focusing on left-hand side of the equation. And actually, we can conduct an eigenvalue analysis. That's the way that we forcing this applied force to be equal to 0. So we're just neglecting the forces because forces do not affect to natural frequencies or corresponding deformation modes. This is in a case of linear dynamics. All right. But we focus in here, small deformation in linear dynamics. Okay. So how it goes. So this is my equation. Remember here, this was a, excuse me, T here, F. It used to be like this. And now I'm just saying that all the forces are equal to 0. So if all the forces are equal to 0, then I can get the features about how the structure, what is the structural natural frequency and the corresponding deformation. But remember, this has nothing whatsoever to do with absolute deformation because I have no forces in the structure. So what I'm going to get as a result is a structural properties, which are natural frequencies and corresponding deformation modes. All right, so if this is what I need to solve, this equation, I do know from the mathematics that the solution can be written in such the way that there is a vector multiplied by E, and then the power I omega here will be our eigenvalue. Let's not put too much attention to this at this time. Let's just substitute the solution to this equation. And you can write the equation. You can write the solution like this. So I have here stiffness minus omega power 2 multiplied by mass matrix. And then the vector, vector here. Now this can be solved by 2 steps. First of all, I can focus on this part. I can set this to be equal to 0. And I can do it by taking a determinant of the matrix, which is a stiffness matrix, omega power 2 multiplied by mass matrix equal to 0. And once I get the solution for my omega, then I can substitute omega back to this equation. Well, it's here too. And then I can solve my eigenvector. Well, this is telling you nothing, absolutely nothing. So we need to practice this a little bit. But here is an important thing, and this is what I'm about to ask from you. Let me check what the timing is. So we have like, let me think, 40 minutes perhaps. Okay, so if I have a finite element model with 10 degrees of freedom, I can extract then natural frequencies and corresponding deformation modes. So if I have 100,000 degrees of freedom, I'm going to get the 100,000 natural frequencies and corresponding deformation modes. We're going to look at videos about the deformation and natural frequencies in a second. But, you can get equal amount of natural frequencies and corresponding eigenvectors than the number of nodal degrees of freedom. So that's how it goes. So again, if you have a complex finite element mesh with n number of nodal degrees of freedom, you can get n number of eigenvalues and corresponding eigenvectors. How it goes, that's we're going to practice in a second. But here's my in-class quiz. So I have here a finite element model of a car, and this car consists of m number of elements, n degrees of freedom. The model can be used to solve how many number of eigenvalues. Question mark is number of elements, number of Nodal degrees of freedom, degrees of freedom, elements minus Nodal degrees of freedom, elements plus Nodal degrees of freedom. Those are the choices. And let me put the Socrative back on. So here's my browser. Okay, what the question mark is. So is it going to be the number of elements, number of Nodal degrees of freedom, number of elements minus Nodal degrees of freedom, or number of elements plus Nodal degrees of freedom? This is exciting. Let's see how well you're performing here. Oh, I got the first answer. I was a bit afraid that you guys are no longer following me. Okay, and soon I'm going to start providing more physical interpretation of all of this, like everything. Everything needs to be clearly explained. And I want to be slow today. I want to go slowly to make sure that you understand all aspects needed to capture this modal reduction and eigenvalue analysis. The eigenvalue analysis is extremely important. Okay, maybe I should move on to the next slide to explain this. Let me see. We do have 13 answers, so it's not that much yet. Again, I see that my head is too big. Okay, I need to keep it here. How could I not block the view like this way? Okay, so game is on again. So we got. Oh my God! Now there's a one guess that says 25%. 25%. Well, that statistically it's 25. So we'll see. That's 25. 25% would tell that no learning at all. No learning at all. That would be a little bit of disappointing. Everything above 25 tells that there is some amount of learning. 100% would be a different story. That would be beautiful learning. Okay, but let me see. I have 17 students, so I'm not gonna get all the 20 something answers this time. I see that I have less guesses too, so maybe some of you are already giving up. Hopefully not, because this is extremely important. And I know that it sounds like not even doable, so this is so chaotic, but this is what the uses opponent in his class entitled as Massing Dynamics. He's explaining this way more deeply and way more in details. So it is something that is often used. It's very, very basics of mechanical engineering. And basics in mechanical engineering, because this is also heavily related to vibration. And vibration, if something is important, is a thing that you guys need to master that in certain level. Okay, so enough talking. 21 answers. So here's my Socrative. So can I put it on? I mean, can I keep on going? Okay, so there's a Yeah, you can still change your answer if you feel that your first guess was not good enough. My personal guess is this one. That's right. 85. 85. So I'm thinking that we're gonna score that high. Yes. All right. So yeah, I think at the last time we got 28 students, and it's the same number here again. So let's show the results. Not bad. And look at this. The colors are back. Colors are back. So we got 55. 55. Was that too late? I wasn't able to follow that. So let's say that not the same winner than the last time, but let's call that a 55. The last guess. Let's put the one extra point. All right. So do we have anything else? 52. Close enough. Close. Oh, we have 56. 56. 56 again. Come on. Same individual that was guessing last time correctly too. This is quite amazing. Okay, YN. I'm gonna explain that in a second. Let me just first make a record about the winners. Yep. So one more winner here. Okay, so I'm done. So YN. So let me take this away. All right. If I have, again, this cantilever beam, or let's say that I just have a beam structure like this. Beam structure that consists of 3 elements. All right. And it consists of 4 nodes. The 4 nodes and the nodal degrees of freedom associated with this nodal location, that's what really defines what will be my size of the problem. Let's say that this is going to have 2 degrees of freedom, 2 degrees of freedom, 2 degrees of freedom, and final 2 degrees of freedom. So it will be 8 degrees of freedom. That means that if I write this problem like this is going to be my number of unknowns. It's going to be 8. It is telling me what are the different ways that the structure can deform. And it's going to be 8 different ways. And these 8 different ways can be solved by conducting the eigenvalue analysis. So that's why this is a correct solution. Number of elements doesn't really make any difference here at all. And these options C and D, they are complete nonsense. So they make no sense whatsoever. So the first one and the second one are the one that kind of make sense. But out of the 2 options, only the number of degrees of freedom is the one that is important. And now I got an information to my YouTube window which says that my bit rate is not good. So how is that you hear me? Should I reconnect my headset? The same problem than last time, and now I know how to change the bitrate if there is a need to do so. Okay, so how is my voice? Is it clear enough? Because I got warning signal in my YouTube studio. So is my voice okay? Normally difficult. So okay, so all right. So now this eigenvalue, back to this eigenvalue. Just going back to the basics. So this is bachelor level things that I'm about to explain to you. If you have a mass that is connected to ground by a spring, this is a system that is considered as a 1 degree of freedom, because we can simplify or assume this structure to be such that it can only go up and down, And how this can go up and down, this can be defined by force, which could be a function of time. And let's say that hypothetically, I'm saying that the force here is having the frequency that is changing. So it's first getting started by the low frequency, and then it's increasing the frequency over and over again. I mean, more and more. And what will happen to this structure is that this mass will follow the motion. Let's say that in a certain, let me change the color to make this more clear. It follows the behavior in a certain way. But once it hits the natural frequency of the structure, then this response becomes to be like unnaturally high. And this is called resonance condition. And resonance condition is the feature of the structure. So it's a feature of the structure, which is a mass and the stiffness. Mass and stiffness combination, when that becomes to be in a certain area, it means that the structure can have a resonance. And particularly if the loading is in the same frequency, the structure is in resonance, and then the response will be very high. So means this. So if I look into amplitude, then then this is a frequency. So when I'm hitting the resonance amplitude, the amplitude is kind of getting to be really, really high. So it's going to be something that you see every now and then when structures are going apart because of the resonance condition. So resonance is something that is really nasty thing. This is exactly what we're computing in eigenvalue analysis. So we're computing the natural frequency. And if I have here, let's say, system that consists of two masses, that would mean that this structure will have two natural frequencies and two different ways that these natural frequencies can, or two different deformations that the resonance condition can take place. So the first one is probably the one that both masses are moving downwards. And the second one is probably something that the first mass is moving downwards and second mass is moving upwards. So those are the two resonance conditions. And they typically, when you're making a drawings about, frequency, the first one is here, the one that they're both moving downwards, that's kind of low. And the second one is probably a bit higher. So those are the ones we're solving by using eigenvalue analysis of finite element models. Let's look at a few videos to clarify the issue. So I have here, oh, come on. What? Why not? This would be important to see. Let me see. How can I play this? Picture. No, come on. Why not? I'm gonna do this I'm gonna send you the link. No, it would be so important to show these animation panels. Why is this not willing to play for me? It looks like this is completely missing. Hold on. Okay, so I'm gonna miss this animation. So I'm gonna place this animation to modal side. But anyway, so I have here a structure that consists of several masses, and then the wire that is connecting these masses. This can be considered as a system with four masses, 4 degrees of freedom. So this is going to have 4 different natural frequencies. And what the resonance condition is, that's going to be described by this video. So I need to leave these videos aside, and I need to revisit these videos. There is a video in older lecture. Okay, great. So great, restart the presentation. So that would be the way to go. So should I close it and open it again? Let me try. In the playlist. Okay. Enable content. Yes. All right, so then I'm gonna move all the way here. Oh, look at that. Yep, it's coming. Multiple degrees of freedom. You guys hear the voice of the video, or is it just me? Okay, not hearing the video. So, okay. All right, so let me explain what's here. So there's going to be two different ways that the structure can deform. This is the first way. All right. This is the second way. So consider these like a degrees of freedom in your finite element modeling. So one way and two way. Now if you have n degrees of freedom system, you can have n different ways. N here refers the number of degrees of freedom. Now, this says 3 degrees of freedom mass spring system. There's going to be 3 different ways. So this is going to be the first mode and associated frequency. And then it's going to be the second. There's going to be a third. Sure, I'm going to send the link to this video for sure, because this is, okay, here's a second deformation mode, then there's going to be a third one. And now this is how it goes. So if you're going to have 1 million degrees of freedom, you have 1 million different ways that the structure can deform. Now, and this is exactly what we wanted to do here. We wanted to identify these ways structure can deform. Oh, this is third. And now I'm going to move on. I'm going to rewind a bit. This is a 4 degrees of freedom. This is, excuse me, hold. Here is a lowest frequency. Oh, okay, so the videos is not behaving well. Okay, so I'm going to send the link. And we're going to move on. So hopefully these videos are behaving better. These are telling how the natural frequencies are. Let me see. How the natural frequencies, excuse me, how the deformation modes look like in a simple tube roll. So these are the possible deformation modes that are extracted using the finite element model. I see that my video is really not sure how well it plays for you. Oh, it seems to be okay. Anyway, so I'm gonna place these videos to someplace in modal side so you can take a look at those a bit later too. But these are the deformation modes that are coming out from the eigenvalue analysis. Now, what I really like to do here is that I would like to explain this eigenvalue analysis to you a bit more in details. Okay, so these are the results. I think that this is the best describing. This is deformation modes of this kind of symbol structure that I'm sure you know what it is. So this is a deformation in this direction, and this is a deformation in transverse direction. So these are the kind of the ways that the structure can deform. The way structure can deform, nothing else. Because I'm keep on increasing or looking at the higher and more complicated ways structure can deform. Some of the ways will look like this, which is for sure not significant for overall behavior of the structure. This is exactly what we wanted to do. So we wanted to forget about some of the complex modes, which definitely contributes very little to overall behavior, like practically no contribution. This kind of contribution may be important particularly if you want to look at the certain details close to the place where hydraulic cylinders are attached. This may be the same, but this one definitely have no value. Not important for us, and this is what we can ignore. And this is the way we can reduce the size of the problem. Okay, so let's look at an example then. Let's look at a little bit, what it means when we're moving from these modal coordinates, nodal coordinates to modal coordinates. And I know that for some reason I'm not happy about my explanation today. I don't know why, but it seems that it's not so clear today. So I'm going to repeat not the whole story, but the highlights of the story next week, Wednesday. All right, going back here. This is my original equation of motion. Gonna change the color to be back in red. Okay, and the problem associated to this is that there is so many degrees of freedom, which I don't like. So I want to reduce the number of unknowns. And the way that I can do this reduction is that I'm going to create the relation between nodal degrees of freedom, these deformation modes, and corresponding amplification. This amplification is the how much these nodes are moving relatively with respect to each other in certain modes. So this one here is a vector, this is a matrix, this is a vector. So once I use this relation, I can express, first of all, so if I'm going to take these drawings away. First of all, when I submitted that to this equation, it's going to be like P dot dot K P force. Now when I multiply that with the transpose of this mode matrix one more time, this is going to be my final equation of motion. And now equation of motion here is expressed in terms of modal coordinates. Modal coordinates. These will be my unknowns. And because the modes, well, depending how they are selected, but if the modes are orthogonal, like they always are orthogonal if you are conducting an eigenvalue analysis, it means that the new inertia, oh, this is, by the way, missing this guy here, a new stiffness will have a diagonal representation, meaning that these mode coordinates, modal coordinates, have no relation each other. So you can just take one modal coordinate and solve that, and knowing nothing about other modal coordinates. And this is very different than when comparing the original finite element modeling, because in original finite element modeling, these mass and stiffness are not diagonal representation, but they are block diagonal representation, meaning that you cannot just solve 1 degree of freedom knowing nothing about other degrees of freedom. This is a great advantage, which we're going to discuss a bit more next week, Wednesday. All right, here's the final thing that I will do today. So I would like to show you how is that we can conduct an eigenvalue analysis. And this eigenvalue analysis will be conducted for a structure, which is a spring structure. So this is essentially a structure like this. Oh. These waves mean springs. And I have here 1, 2, 3 elements. And 3 elements are connected together in 4 nodes. Each one of the nodes has a 1 degree of freedom, just 1 degree of freedom, because the nodes can move left and right, nothing more, left and right. These 2 can move left and right, and that's about it, left and right, and left and right. Now, when you construct stiffness matrix for this entire structure, it can be, or it actually will take a form like this. How this will take a place, that's gonna explain some of the details to you next week. But this is going to be your stiffness matrix. And the stiffness matrix consists of 4 columns, 4 rows, because nodal degrees of freedom. Your mass matrix, that too will have 4 rows and 4 columns because of the 4 degrees of freedom. All right. Now, what I can do for this structure is that I can take a look at the feature of the structure by conducting an eigenvalue analysis. And it goes like I explained in one of the earlier slides. So I'm going to first compute the eigenvalues. And it's going to be simply by taking my stiffness matrix, my mass matrix, and multiplying that by omega power 2, which is here denoted as a lambda. And taking determinant of that. Of course, you know, in real life, this is not how it's being solved. There's going to be more sophisticated way, but I want to keep this simple to show it you how it actually works. So now we're going to take a determinant out of this one here. When you do it, you will get the fourth order polynomial. Fourth order polynomial will have a zero value in 4 different locations. And those locations numerically are 0, 12, which is just the value, 60, and 120. 0 here stands for rigid body motion, because remember the structure is like this. There is no boundary condition whatsoever, so it can, the structure as a entire structure can move left and right because of the rigid body motion. And this solution here stands for rigid body solution. Now the others are defining the ways that the structure can deform and the frequencies associated with that. And how you can get the natural frequency? Well, this is the formula to compute that. But let's just call them as a numerical value 12, 60, and 120. These are the eigenvalues, resonant frequency, if you want to say it this way, which would be okay. All right, how is the deformation modes? Well, we can get the deformation modes by substituting these eigenvalues one at a time to this equation, one at a time. So let's get started from 12. So I'm going to substitute 12 here, and then I'm going to solve this guy here, this vector here. So it's going to be a system of 4 equations, 4 unknowns, because these are referring my nodal degrees of freedom. And the solution is going to be like this. Not solution, but you know, these 4 equations that I need to solve, they're going to look like that. So it's going to be a system of algebraic equations. And once I solve these unknowns, I will get the relative motion, the way structure can deform. Let's try to depict that. You know, here is my original structure. You know, the way the structure deforms here is that the first node is moving -2 direction. So it's going to be roughly going here. Second node is moving -1 direction. Third one is moving 1 direction. And then this one is moving plus. Let me see if this is still visible. Where the heck is my browser here? Not really visible anymore. Okay, let me make another drawing here. So this guy is moving here, this guy is moving here, this guy is moving here, and this guy is moving here. So it's symbol deformation. So it's like extracting, distracting, like this, constructing. This getting longer and shorter, getting longer and shorter. That's the first deformation mode. So it's very, very simple. And it's associated that frequency that you can get by using the value of 12. All right? Can we look at another deformation mode? Yes, we can. So we can look at the deformation mode associated with the other eigenvalues by simply substituting the new eigenvalue to this equation and solving the new vector. The vector tells you the way structure can deform. And now it's extremely important to understand that this is nothing to do with their absolute position. So you cannot measure the absolute position. This is just a relative position. Because this solution here, or let's put it here, these values that you get as a solution can be multiplied by any scalar value you want, and they still fulfill the original equation. And this multiplication, that's, by the way, is called scaling. So you can scale these numbers however you want. So you can multiply them by 100, and it's going to look very radical. Still going to fulfill the original equation. Or you can multiply that by 0.001, and it's not looking bad at all. So it's just the way the structure can deform. Way the structure can deform. Okay, let me see. Here's my All right, so I don't have any other deformation modes computed here, but I will do that a bit next week. Here's my final question to you. Physical interpretation of eigenvector. Maybe a little difficult, and I see that I need to relocate my window again. Here. Physical interpretation of eigenvector. This deformation mode. What is telling you? Relative displacement of nodal degrees of freedom. Absolute displacement of nodal degrees of freedom. Strain distribution within the structure. No clear interpretation. This is difficult. This is difficult. So now if we're going to get success rate more than a 50, I'm going to be very, very happy to see that. Okay, so let me put my Socrative back in operation. So it's on now. So please take a look. And I'm going to repeat the story, highlights of the story next week, Wednesday, like carefully, extremely carefully, because we do need to understand this in details to be able to use this in modal reduction, reducing the size of the problem. And again, the reducing the size of the problem gets started in a way that you are modeling the structure by using finite element model. The equation of motion for this kind of structure will be like this. And then what you're going to do is that you're going to move from these nodal coordinates to modal coordinates. And what these modal coordinates means, what this deformation means here is that, these are the ways that the structure can deform. Not the absolute values, but the relative displacement between nodal degrees of freedom. All right, so I'm not sure if I can explain this in a clear way today, but I'm going to repeat this whole story next week, Wednesday, and I'm going to put an effort to make this as clear as possible. So, game is back on. And once I'm done with this in-class quiz, I'm going to close for today. And there's, of course, this opportunity to discuss with me in Teams. So, now this goes in a, how can I get rid of this? Okay, my guess about the success rate is not too positive. I'm guessing this. Where is it? Here. 45. Yes, 45. Because I'm not at all happy about the way that I was able to explain this to you. Because some reason, I need to make more slides. I'm kind of like looking at the core content, and somehow I think that this will be the way to look at that. And then how to get these deformation modes. That's something that I need to work with a bit to make sure that the story is fluent. Let me practice. Let me practice this one more time while you're guessing your correct answer, while you're putting your answers to Socrative. So, a little bit unclear writing, but this is my equation of motion. And what I'm doing in my equation of motion is that first I'm going to take a look at these structural features. And when I look in these structural features, I can conduct an eigenvalue analysis. An eigenvalue analysis are eigenvalues. They're going to be equal number of eigenvalues than the number of degrees of freedom, which are like these resonance frequencies. And each one of these eigenvalues will have an eigenvector. An eigenvector tells me how the nodes are moving with respect to each other in that particular resonance frequency. All right. Then what I can do then is that I can build a matrix from these deformation modes. So this is the first one. And this is N1. This one here allows me to find the relation between nodal coordinates and modal coordinates. This MP here, there will be equal number of P's and there will be these modes. And they are telling me how much the one deformation mode is contributing to final response. That's what I wanted to do. And now when I'm using this relation in my equation of motion, I can write everything in a very condensed, simple form like this. Like this. This is going to be diagonal representation. This is going to be diagonal representation. So it's very easy to solve these P coordinates. And once you get the P coordinates, then you can go back to the nodal coordinates by using this relation. All right, but I need to work with this explanation one more time to make sure that it's fluent. And I'm not going to use the drawings because the drawings and my handwriting is not clear. But back in the game. Oh, hold on. I did something stupid here. What is this? I got a message to my headset that is disconnected and now connected again. All right, so let me see. Here's my in class. 24 answers and success rate is. Come on, this is really nice. 88. Think about it. I was guessing 45, but it's 88. Okay, 88. Did we get the winners? We did not, because you guys are all guessing so low numbers that no winners. No winners. The closest is 78. 278s. And again, these guys that are always guessing correct values. Oh my God, I don't know. They just seem. Oh, there's a 190. There's 190, but it's 90 is the one that will be considered as a winner. Nice. Okay, so I'm gonna close today's lecture. I'm gonna close the streaming, close the recording, and momentarily I will send you a link to a Teams session so you can meet me in a Teams after a couple of minutes. All right, and please remember to be here next week Wednesday because we're gonna look at the ways you can practice yourself to read an exam. And again, the written exam will take a place, as you can see from the chat window. It will take a place on, I think it was somewhere in the very beginning. Okay, 2nd of March at 4:15 p.m. 4:15 p.m. to 7:15 p.m.